For the next few videos, we're going to turn our attention to capacitors and capacitance. So we can use a similar procedure that we just saw for our resistance for our capacitance. And we're actually going to see we have another option as well. And so I'm going to talk about both of those. And then in the following videos, we're going to see an example of how to use each method. So going back to our general capacitor equation, we know that capacitance is equal to charge over voltage. And so we can relate those to some expressions that we've seen previously in the notes. So this is going to be epsilon times the surface integral of E dot ds. And so previously we've seen that as D dot ds. And so I've just used our relationship that our electric flux density D is equal to epsilon E. And we know that our voltage is the line integral of E dot dl. And because we're only interested in the voltage magnitude, I'm going to leave off the negative sign that we normally have out front of that. So this would be our general expression for our capacitance. So another note too is that in general, our capacitor is going to have two or more plates that are going to have equal but opposite charge. So generally, a capacitor must have two or more plates. And so we're going to consider primarily in our examples just simple parallel plate capacitors, although later on we are going to talk about some more complicated structures, not necessarily complicated, but such as a spherical capacitor and a coaxial capacitor or a coaxial cable. So these plates have to be carrying equal but opposite charge. And so the first sort of set of steps we're going to talk about doesn't actually utilize our boundary value conditions, but as we're going to see in a later example, we definitely can still use that boundary value approach. So in this sort of more general approach, our first step is still going to be to choose an appropriate coordinate system. So choose appropriate coordinate system. So the second item is going to be let the two conducting plates carry some arbitrary charge plus and minus Q. So let our two plates carry charges, and remember they have to be equal and opposite. So we'll say on one plate we have plus Q, and on the other plate we'll have minus Q, and that's just some arbitrary charge. So third, we can determine our E by using either Coulomb's or Gauss's law. And so we talked about that, of course, in a previous unit. If we have symmetry in our charge distribution, then Gauss's law is going to be easier. But of course, Coulomb's law is the more general one. So for 4, once we have that done, we can find the magnitude of V from that expression we had before. So our magnitude of V is, of course, the integral of L, our line integral of E dot dl, rather. And once we have that V, and we know the assumed charge that we started with, so that's just going to be the magnitude of these charges, so we sort of drop the plus or minus, and we're just looking at the Q then, we can go back to our general expression. So in step 5, we say we find our capacitance C from C equals Q divided by V, where again, the Q is what we assumed on the plates, and our V is what we found by applying Gauss's or Coulomb's law, and then ultimately using that line integral definition of our voltage. So as I mentioned, we can also assume, or we can also use our boundary value conditions. So let's say we want to do this with our electrostatic boundary value method or our Poisson and Laplace's equation. In that case, what we're going to do is we're going to assume some voltage across the capacitor, and we're going to determine our Q from the voltage. So determine Q from V. And again, because we're talking about a conductor, we're going to be using our Laplace's equation. And so I'm not going to go through and enumerate each of those steps as we did with our resistance, but as I mentioned previously, a couple videos from now, we're going to look at how we can actually solve the expression for a parallel plate capacitor's capacitance using this boundary value approach.